Hello and welcome back. In this video, we're working through an example of graphing the level curves of a function of two variables, of the graph of a function of two variables. In this one, we're looking at the function f of xy equal 2 plus sine of x minus y. So this is a pretty weird looking function, certainly not a quadric surface, so we have to better understand this by looking at its level curves. So one thing I can do to start this out is figure out, just like we did in the last example, we did this analysis up here to figure out like what sort of heights, what should my step size be for graphing these level curves. Here z had to be between 0 and 1, and so we went by steps of 0.1. Let's try and do that same sort of analysis here. So I'm just going to set this equal to a constant z naught. Right, z naught being our arbitrary constant. So let's do it up here. Z naught equals 2 plus sine of x minus y. All right, so I'm going to solve here for sine of x minus y. So I get sine of x minus y equal to z naught minus 2. Now I'm going to remember domains and ranges of my functions, or rather just ranges of the function sine. Remember sine of anything, sine of u, let's say, is always between -1 and 1. For any u, right? That's how our sine function works. So what that tells me is this output has to be between -1 and 1. So this tells me that z naught minus 2 has to be between -1 and 1. And that tells me that z naught, adding 2 to all sides of this, I get z naught has to be between 1 and 3. So we might go by 0.2s if we want 10 level curves. I'm going to graph the level curves. I'm just going to do 3 sets, and we'll see why. Graph level curves, I'll do z naught equal 1, z naught equal 2, and z naught equal 3. I'm going to graph these level curves, so just 3 curves. All right, so z naught equal 1, I'll get sine of x minus y equal 1 minus 2. So when z naught equals 1, we'll get sine of x minus y equal to -1. And now I have to ask myself, all right, well, how do I solve this? How do I figure out this curve in x and y? Well, I need inverse sine of -1. And remember that we don't just want the inverse sine, the range of the inverse sine function, but we want any possible values of x minus y such that sine of that is -1. So we want to get all solutions. We need all solutions to this. Need all solutions. So when is sine equal to -1? Well, that happens when the angle is, pi over 2 is straight up. That gives me sine of 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And then any multiple, and if I add any multiple of 2 pi to that, I'll also get the sine of that angle being -1, right? And there's no other values that do that. So that tells me that x minus y is equal to 3 pi over 2 plus some multiple of 2 pi. So I'll say 2 pi k here for some k. Or actually not for some k, but for any k. Any k, and that's an integer. I don't know if you know the symbol for integers. It's this bold-faced z. So here k is an integer, and we have x minus y equal to this. So that tells me that, so let me just pick a few k. So let's say k is 1. K equal 1, no, let's do k equals 0. Let's start with k equals 0. I get x minus y equal 3 pi over 2 plus 0. And so that gives me y equals negative x plus 3 pi over 2. So I'll graph that. Let's do, what if I do k equal 1? Then this will be 3 pi over 2 plus 2 pi. 2 pi is 4 pi over 2, so that'll be 7 pi over 2. So I'll have x minus y equals 7 pi over 2. And so that gives me the line y equals Wait, did I do this one right? No, this shouldn't be a negative x, right? No, this should not be negative x. This should just be x and then minus. I had my signs mixed up. Maybe you caught that. X minus 3 pi over 2, right? Subtract that over, add the y over. Yep, I get that. Here I'll get y equal x minus 7 pi over 2. If I do k equals negative 1, negative 1 for this, I'll subtract 2 pi. That's 4, so that'll be minus pi over 2. So I'll get y equal x plus pi over 2. I'll just do these few values of k. So this is all the same level curve. I get a bunch of lines. I get a bunch of diagonal lines, lines of slope 1 with various y-intercepts. So I'm going to mark off here up to 2 pi positively and negatively. And then I'll go, so this will be pi then. This will be 3 pi over 2. And this will be pi over 2. And the same thing down here. Negative pi over 2. Negative 3 pi over 2. So keep in mind, I'm only knowing how to set up my graph of this thing after doing quite a bit of analysis. And then since these are all lines with slopes of 1, I'm going to do the exact same scale in the x direction. So 1, 2, 3, 4 up to 2 pi. 1, 2, 3, 4 up to 2 pi. Pi. This is pi. This is 3 pi over 2. This is pi over 2. Same thing over here. Negative pi over 2. Negative 3 pi over 2. And negative 2 pi. And I'm going to graph these all in red. So z naught equal 1. This level curve at this height, I'm going to do in red. And it's this collection of lines. So when k is equal to 0, I get x minus 3 pi over 2. So that's here. And I can do this well. I'm going to use a ruler for this. Negative 3 pi over 2. Since it's a slope of 1, I should also intersect 3 pi over 2 here. There, that looks about right. So that's at z equal to 1. We also have x minus 7 pi over 2. That would be down here, right? 2 pi over 2 is, or 2 pi is 8 pi over 2, or no, sorry, 4 pi over 2. So maybe that one's not good. I won't picture that one. That's going to be too far down. That's out of my scope. That's okay. But then I did have when k was negative 1, right? When k was negative 1, I have y equal x plus pi over 2. So I could do that one here. And so those are both at a height of 1. Interesting. So I like this example because it shows that our curves, our level curves, do not have to be connected. Curves don't have to be connected. They could be disconnected lines like this one, or maybe they're, circles that are disconnected from each other. That can happen. So that was at z naught equal 1. Let's, how about in blue, we'll do z naught equal to 2. So over here I'll set z naught equal to 2. And that'll give me what? Sine of x minus y equal to z naught minus 2, so equal to 0. So now I have to ask myself, when is sine of something equal to 0? That happens at angles of 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, any multiple of pi. So this tells me x minus y equals any multiple of pi. And so that gives me y equal x minus k pi for any k, for any integer k. All right, well, I can do that. Let's see. So multiples of pi. I get lines, again, slopes of 1. So that's multiple of pi. Here I go another multiple of pi. I get another diagonal line. We could do this multiple of pi, right? 2 pi is an integer multiple of pi. Let's do pi up here. Here's another multiple of pi. And here's another multiple of pi. So that one gave me a lot of curves, and those are all, I'll mark all of those. Those are all at height of 2. And then the last one we'll do is z naught equal to 3. And this is why I'm only doing 3 heights here for my level curves, because each height is generating a number of disconnected lines. So the last one is z naught equal to 3. I've run out of room, so I'll jump over here. So z naught equal to 3. So this gives me sine of x minus y equal to positive 1, z naught minus 2. So yeah, that's positive 1. I ask myself, when is sine of something equal to 1? That happens at pi over 2, or I could add 2 pi to that or subtract 2 pi to that. I get x minus y equal pi over 2 plus some multiple of 2 pi. So 2 pi times k for any k. So, all right, so I'll graph these then. So I'll start at pi over 2, minus pi over 2, right? Pi over 2. Yeah, what's going on here? I have x minus y, so that means y equals x minus pi over 2 minus 2 pi k for any k. So that's pi over 2, so I'll start at negative pi over 2 for my y-intercept, and then I can move either up or down 2 pi to get the other curves. Right, we're seeing these patterns here now. Makes graphing it easier. So here I am starting at a y-intercept of negative pi over 2. I get a line. I can add 2 pi to that. That'll put me over here at 3 pi over 2. Right, negative pi over 2 plus 4 pi over 2 gives me 3 pi over 2. And then I can also go another 2 down. That would happen down here. So maybe I can graph that one too at negative 5 pi over 2. And those are all happening at 3. So it looks like the peaks of this thing are happening periodically, right? And the troughs too, right? 1 is my lowest value I can get out of this. 3 is my highest. So I'm having troughs along the red lines, peaks along the green lines, and then in between I have this height of 2. So that's sort of the middle ground. All right, this one's harder to visualize. It makes sense that we have this periodic nature to it because we have a sine involved, and that's a periodic function. So if you can almost imagine it along these diagonals, if I sort of draw, oops, I don't want to quite do that. If I think of this like a perpendicular to these curves, like what's going on perpendicularly, I should get a copy of sine. Right? Because it's going up and down and up and down. So imagine these at different heights, I get a copy of sine. So it almost looks like, for visualizing this thing, that if I have these off diagonals, I get copies of sine 2 plus sine, right? I get copies of 2 plus sine. Something like that. I get some kind of sine curve along the diagonals, and then it's sort of extruded out along the positive diagonal along this line y equal x. All right, so let's see what this thing looks like. Oh no, please don't delete all of that. Oh no. All right, well, I gotta delete my level curves. That's a bummer. There's the figure I get. And so you can see some of these level curves, like up here, this is where the peak was. The green ones are happening up here at the peaks. The red ones were happening down here at the troughs, and then the blues, right, there's another one at the trough, and then the blues were happening as I ascend. That's this guy here on the other side. This guy was one of the 2s, and so forth. And there's our level curve. So there's, if I look sort of along the diagonal, I see a copy of just a sinusoidal wave. All right, that's it for this one. This one's pretty challenging, so I applaud you for sticking with me.